Okay, we're gonna get started here. Sir, could you close that door on your way in? Thank you. Oh, attract a few more people. Oh, I guess there we go. Thank you. I hope you're all interested in learning about hybrid systems. If you're not, then this may not be the place for you, but I hope you are. My name's John Rath. Christine calls me JR simply because we've got too many Johns, or had too many Johns, on our board of directors, and it got really complicated. So I defaulted to JR. Today we're going to talk about hybrids, but first I need to give you the spiel about CEUs. Some of you have already heard it, but if you're here for CEUs, at the end of this session, please come on up to this table to my right, and we're going to need your signature if you're already registered. If you're not already registered, you can still get your CEUs. We just need you to sign a different sheet and go see Christine at the registration desk and take care of the business side of that. What impressed me most about our two presenters today is that collectively they've got 50 years of experience between them. Rob has 32, and Joe has 18. Did I get that right? Yeah, so we got 50 years of experience. I hope everybody takes advantage of that, and you get your money's worth out of these two gentlemen. Just a quick brief so you know who is doing the presentation. Rob's been with public, private, program, and project management. Public, private, program, and project management, lots of P's, for a lot of those 32 years. Joe has got lots of experience working in clean energy master plans, net zero carbon roadmaps, and both of these gentlemen know New York State pretty well, I guess, because you're working with the SUNY system, you're working with NYSERDA, working with the DEC. So I don't know how we're going to cram this into an hour, but we're going to give it a shot. Please give a warm welcome to our speakers.
Thank you, John. Okay, so let me just start by introducing myself. I'm Rob Neimeier, based in Syracuse. So Ramboll, if you haven't heard of Ramboll, if anybody in the room remembers O'Brien and Gear, anybody remember that company? No? Not, oh, all right, a couple head shakes. Is this live? Sophie, can you hear me? Okay, good. So if anybody remembers O'Brien and Gear, we were acquired by Ramboll back in 2019, 2020. Ramboll is based out of Copenhagen. We're international, like 18,000 people worldwide, 35 countries, and lots of offices all over. What's important about what we're going to cover today is a lot of the decarbonization planning that we've been doing in New York State, like John said, for SUNY. Even more, really.
It's live, but I think we need just a little more volume.
All right. Test, a little louder. All right, got to get close to this one. All right, normally I don't have a problem with this. So the decarbonization planning, we're working for NYSERDA, as John mentioned now, doing a thermal energy network study throughout the state, and we're also helping the Department of Public Service on the U10 filings, of the technical review of the filings. So we're going to try to bring a lot of this, the decarbonization planning that we've been doing, to this discussion. So learning objectives for this is holistic energy system planning. That's cost effective. I think we're going to keep coming back to this. I think you heard some of that today. It's threaded into many of the presentations that we do, is pragmatic and cost effective transition. We've seen this from the influence from our colleagues in Europe and what it's taken for many, many years that they've been working on this. And ultimately, it has to be cost efficient to the end consumer, particularly if we're working in disadvantaged communities. Technology and cost consideration for base load and peaking. This has come up most recently in a lot of the U10 filings, but also as part of how we approach planning, and Joe will cover that. Thermal energy storage, it's started to get talked more about, I should say, in the last year or so. Most of the time, the default was to battery storage, and thermal energy storage will be extremely critical with a future renewable grid that's intermittent energy. And some short-term and long-term energy transition considerations. So we'll talk about planning from a holistic standpoint, baseload peaking, the role of thermal energy storage, making sure we got enough electrical capacity. If we learned anything from the SUNY work of the campuses, and we did 8 of those over the last 18 months, is some of them were in really good shape and had capacity, but if you were going to full electrification, they didn't have the capacity. So you either need to upgrade at the campus level or you had to upgrade at the utility level. And then we'll cover some project examples. So just from and kind of taking off some of what we heard in the opening remarks this morning, as well as what we heard at the keynote, this is about thinking of broader systems approaches to thermal energy networks, district energy, community thermal networks, whatever the terms are going to be that we're going to use. But it's about sector coupling. It's about what's in your community. If we look at how energy planning has evolved, at least in the time that I've been working on it, which is about 2008 up through now, and it was very energy efficiency focused all the way up through probably 2017. And then right around that time is when decarbonization buzzword was out, and then we had the CLCPA, and now here we are. So thinking about what we might otherwise have thought in the past of a building, and let's make that building geo. Then we started to think about, what about the campus? Let's make the whole campus geo and think about a broader system. And now it's really about, what about that campus within the community that it resides in, and what about a municipal-based system? So we're going to be showing those types of examples with you today. So where are these are just the various decarbonization influences and considerations. I'm not telling you anything that you don't know. We're just identifying, there's all sorts of goals out there around hitting targets. We think the goals need to be equitable, flexible, and they need to have some resiliency to them. Heat sources, lots of different ones. So whether it's air, ground, wastewater, waste heat, cooling, all sorts of different considerations for thermal networks. The equipment, heat pumps, we got to think about refrigerants, we got to think about storage, the types of piping we're going to use, how we're going to integrate all of this. What's the impact on the grid? We heard a lot of that at lunchtime and throughout the morning sessions. And we've got some really cool slides to show you on what does an intermittent grid look like in Denmark, and what does it look like with the renewable, and then what does the demand look like over that? Funding, where's that coming from? Workforce development, the recession's on that today. Alternative fuels, what are we going to use for peaking and backup? What's the role of renewable natural gas in the future? Biofuels and otherwise. And then just, sometimes a bunch of uncertainties in terms of, got natural gas constrained areas, moratoriums, electrical grid impacts, and otherwise. Okay, Joe's going to pick it up.
All right, just going to go over baseload peaking and backup strategies that we've looked at for some of our clients here. So what do we mean by baseload and peaking? So if you look at a heat load throughout the year, and this is not a seasonal profile, but if you sort from highest to lowest throughout the year, you end up with, on the left, what your peak load is. And what we're trying to do is design our base load around more higher capital expenditures, so you're utilizing that asset. It's going to be a cheaper fuel, so we'll show that in a couple of slides, but utilizing more electric-based equipment for that base load production. And when you size that base load for about 55% of your peak, you are covering typically around 90% of your annual load. And that's a bit of an optimizing sequence that needs to go on in order to figure out what's that optimal sizing. Is it 55? Is it 40? Is it 60? But basically what this is doing is that we're reducing the cost of what that baseload equipment is. We're not sizing it for 100%. So if you're looking at a geothermal system, it's half the cost of what it would be if you were to size it for full geothermal and only utilizing that peak for that 10% of the year. So then again, sizing that peak production for the remaining load, that only covers 10%, but you're going to be using lower cost equipment, and generally it's a higher cost fuel. Right now that may not be the case with current pricing, but as more renewables get put into the grid, that cost will change, and fossil fuels will likely increase in cost. And that's what we're seeing, over in Europe. So geothermal, I know this is a geothermal conference. It's one of the heat sources that we look at, but looking from a holistic standpoint, we try to pick out what heat sources are available to the different clients we're looking at. So it's not just geothermal, but you can have an industrial waste heat, wastewater treatment facility, so capturing that heat as it exits the water treatment plant. Heat rejection from cooling, so using the cooling from the buildings and just passing that heat rejection off for space heating. Refrigeration, so if you have a large refrigerated warehouse or some kind of refrigerated manufacturing process. Aquifer thermal energy storage, we'll show some examples of that in a little bit. Your traditional geothermal, ambient air, using sewer water, so sewage leaving a building or collected from multiple buildings before it goes to a water treatment plant. Surface water, rivers, lakes, electric substations, so those are depending on their loading, they constantly have some kind of heat generation that you can capture. And also subway tunnels if there's dewatering stations that have a pretty consistent flow that we can capture heat from. So our process, we start out with a technology screening, just looking at what technologies are applicable to the client we're looking at, or the campus or the community. So electrification technologies, that would be that base load. We're looking at heat pumps, whether that's a geothermal or air source or wastewater, whatever the source is. And it could be multiple sources. You could use that same heat pump and just change what source you're grabbing from. Electric boilers could also be an option, and then incorporating fossil technologies for that peaking scenario, and backup also. So you're looking at natural gas or fuel oil, or it could be, some kind of renewable natural gas also, or biomass as well. Renewable technologies, if wind and PV could be incorporated into those sites, and then always adding on thermal energy storage. So we'll show a couple slides here where when we store and when we discharge from those tanks. So as Rob alluded to, here's some images we have from our friends in Denmark. So this was in 2015. The two graphs are the same. We just overlaid what the demand is. And this is just the renewable generation. So, renewable is a kind of a policy term, but they do include waste and biomass in their renewable, as well as wind and PV. But you can see there's very few periods where they're generating more than the demand. There's a couple spikes there that go above the demand, but not much. And then any of the white space you see where it's under generating, that's going to be fossil fuel generation. And then comparing that to 2023 as they build up their system. I'm showing this because, this is an existing country that is one of the leaders in renewable energy. It's what New York is aspiring, and hopefully will surpass this. But you can see as they build up their renewable grid, there's a lot more hours where they're generating more than what their demand is. So that either has to be exported, curtailed, thermal storage, battery storage, or some other type of curtailment. And then there's also production when there isn't enough wind or solar, where you're going to be producing from the fossil fuel. So those dips there, you'll see the white spaces would be fossil fuel generation. So the need for energy storage, you can see here's February 2023. You'll see some periods, if I can get that pointer working, some periods where we're generating more than what the demand is. So that has to be curtailed or exported, or with communication between thermal networks and the grid, you can tell those thermal networks to charge their thermal storage during these periods. And then when you get periods where the renewable production is less than the demand, instead of utilizing electricity that's generated from fossil fuel sources, start to dispatch that thermal storage. There's going to be periods where you're going to run out of the thermal storage and there isn't enough wind or solar, so you're going to have to start relying on those dirtier fossil fuels to run your heat pumps, but it's minimizing those periods of when you're using more dirty electricity. So storage is going to be necessary to capture that renewable energy. It's going to reduce the transition costs and speed up the transition from fossil fuels to electric heating.
Yeah, if you go back up. So, yeah, any of them is fine. You've heard Joe mention fossil fuels a few times in this. And, in the state we have, it seems like we have two camps largely of we're shutting off fossil by, in 2 years, or it needs to stay going, and both sides have their, points. We can tell you that from the experience of Denmark, from the experience of Europe, they still are using, like Joe was showing, when the wind isn't blowing, the sun's not out, you have to produce somehow. They have a lot more biomass. Their patience and tolerance for not in my backyard is a heck of a lot different than it is here. So they do use gas. They are looking for alternatives all the time, whether that's renewable natural gas or otherwise. It's important from the campus work that we've done. For SUNY, for example, just to use them as an example, they've got existing assets. Most of the campuses that we did master planning for, they already have thermal energy networks. They're district systems. They're older generation systems that are steam, high temp hot water, medium temp hot water, and they're looking to reduce that. So they've been in the business of district energy for a long time. They've got good plants, some of them. SUNY Buffalo State's a great example. They just finished a $25 to $30 million steam plant in the last few years. Now, knowing where we are now, would you design a new steam plant now? You'd probably rethink that one, and you'd also rethink the distribution piping that you're using on the campus to meet your long-term goals. So I think we need a robust debate or discussion on what does the transition look like. As I mentioned, Denmark's been working on this for 25, 30 years, and gas is still part of their solutions, at least for now, but they're constantly working on it. So transition's gonna take time. We need to be working with some of the assets that we have, particularly if you've already spent money on those assets and they got a lot of life left in them. It's about trying to do the transition economically while we're reducing. And if we're achieving, like through what Joe is showing on the baseload approach, we can get to arguably 85+% reduction by just focusing on that baseload. That's a big economic consideration than trying to cover 100% right now. So, just some aspects.
Thanks, Rob. Electric capacity assessment. So it's really important to look at not just the grid capacity, but what's the capacity at the building or the campus or the community. So do they have the right infrastructure there to handle that increased load? So we'll get into this chart a little bit more in an example, but basically looking, all right, what's their existing load? What are we adding to that? And what's their capacity now? Do we have to increase that substation, or the building transformers, or will they be able to handle the current load because they were designed for that? Also, redundancy needs to be taken into account. What's their take on redundancy? If we're gonna still be, within their capacity limits, but now they have no redundancy, does that fit their needs, or are they fine with that? If the substation goes down and they have no redundancy, it may not be a good thing. So that needs to be taken into account as well. All right, and then we're gonna get into some more specific project examples.
I'm told that John likes this changed out, so this is why we're doing this. Okay, first quiz. Who can pronounce this? What's it sound like to you? Come on, somebody do it. Tarnaby? I thought I heard that. Tornboo. So, Tornboo. So it's a municipality in between the city of Copenhagen and the airport. Okay, so mixed use facility. Sorry, just remind me to get down here if you're not hearing me well. So mixed use facility of commercial, you can see an aquarium there, hotels and office space. It is part of a existing district system that's tied to Copenhagen, but there's a wastewater treatment plant there, has heat pumps. You can see the capacities there for 4.5 megawatt of cooling and 6.2 of heating. And they're expected to do aquifer thermal energy storage there. It hasn't gone through design yet, but that will add an additional 2.8 to this area. And so they'd have, on a hot day, 10 megawatt need of cooling capacity. This is a project that won the European prize for innovative heat pump in Europe. So as I mentioned, it's tied. So when we were talking about sector coupling, the examples that we're going to share with you are kind of just to help us all think kind of broadly about the energy transition and then what's around us when we're doing our project work and our design work. So it complements the existing district system. So during the summer, heating is going to be produced from production of cooling. And then during limited cooling demand, heat would be extracted from wastewater. Talked about the aquifer thermal energy storage that's planned, heating in the winter while cooling the groundwater, and then in the groundwater you're getting a source of free cooling in the summertime. This is where thermal energy storage comes into it. So you've got a 520,000 gallon tank. That's used so when you've got abundant renewable in the grid, you're going to be looking for times to charge those systems because the prices just go basically to zero. When it's abundant and there's too much in the grid, the prices just plummet. And at that time, you're either creating heat, chilled water, or hot water to store it and use it at different times when the prices go back up, like those dips that Joe was showing. And you might not get days out of this. You might get 8 hours plus or minus, something like that. But it's for that kind of flexibility, and it's for operational optimization. Meta data center. This is Facebook, formerly Facebook. This is a city in Denmark called Odense. It's birthplace of Hans Christian Andersen, who wrote The Little Mermaid, amongst many other things. It's a fairly good-sized city. And you can see down to the bottom right is the location of the data center relative to the central plant, which is the main district, which is way up by the red arrow. So this, in Odense, the district heating network is made up of a lot of different things. You can see down on the bottom left there. So coal, combined heat and power, has been in there for a long time. So they're still looking for ways to move off of this, and that's eventually going to be replaced with heat pumps, electric boilers, and biomass. Straw, they call it straw, so it's biofuel. It could be wood chips or otherwise, but oftentimes it literally is like straw. Waste heat. So They have a lot of waste energy plants that are tied to the district energy systems. Not always is quite a conversation that everybody wants to have, but there's a lot of heat that happens from a waste energy plant that's otherwise just gone up to the atmosphere. So they use that and tie that into it. Wood chips, they still use oil and gas for those peaking times that we talked about, and small scale industrial heat. So you can see up in the top right-hand corner there, that's what the district system looks like scattered throughout the city. Those blue areas are different peaking and backup plants that are online that are balancing out the network. And then Meta got added to this district system. So you can see renewable energy coming in from the wind turbines. It's largely wind there, obviously. They have the data center. The data center has the hot air that's going over the servers, and it's hot water is heading over to the heat pump plant, and it's getting bumped up, and then it goes out to a district thermal network, and then it comes back. So you can see the kind of what the loops look like. So about the plant itself, I think the bottom is actually, it looks like that. I did visit this in 2019. It's really cool. And the size of the data center is just absolutely immense. So you can see there was phases 1 and 2 of the data center build out and this project. So that started with 85 and then another 51. So 136 million BTU. It's a pretty sizable amount of heat. What's interesting is on the district heating is going out at 167, back at 113, so there's a really big delta across it. So the heat's being used really well. And then in Meta itself, supplied at 59 and goes back at 81. And Joe's going to talk about SUNY Oswego, bring it kind of home to you.
Okay, getting back to that holistic planning approach, we wanted to look at SUNY Oswego and what resources they had available to them. Obviously, right there on Lake Ontario, that's a huge source right there for heating and cooling. But also, it's got a lot of green space, so geothermal was definitely an option. But adjacent to the campus is, there's an electric generating plant. Yep, there's an electric generating plant right next door that could also be utilized. It also has a water intake from the lake. Adjacent to that also is electric substation transformers. A lot of heat there. They weren't as loaded as we'd like to see, so there wasn't as much heat to grab from that as we thought. But then again, another plant adjacent to that wastewater treatment plant, and the water's being rejected right to the lake right there. So that was another heat source that was right next to the campus. And then we also looked at not just bore fields for the open space, but what kind of renewables could be put on the land that they would like to see, wind turbines and ground mount solar, as well as rooftop and carport solar. So we looked at a bunch of different configurations for them, looking at their business as usual and their existing steam-based system, but then also looking at a clustered approach where there's multiple central energy plants located across campus that serve multiple buildings, kind of like small community heat pumps. And then also looking at doing one large centralized system that would produce their heating and cooling needs. And they were all two-pipe systems that we looked at. They currently operate, seasonally, where they shut off their cooling. So they were interested in looking at, maintaining that operation. When you're digging holes in the ground and laying pipe, it's not that much more to lay 4 pipes, but it was a little bit of a cost advantage for them in that case. In all cases, we looked at a base load and peaking, that chart we showed before about the 55-45 split. But then we looked at different peaking options, whether you wanted to go all electric with electric boilers or stick with your existing assets with the fossil fuel boilers. In all cases, maintaining those fossil boilers for backup purposes. So if the grid goes out or the heat pumps go out, you still have capability to produce heat. They are a area of refuge for the area if there's natural disasters. So they wanted to maintain that stability and reliability. But then heat pumps would produce all the cooling in addition to existing chillers that they have. And then thermal energy storage we looked at for all cases. Can't get this to go. There we go. So how we split the campus up, we looked at these clustered approaches. On the west side there is kind of their residential heavy area, and then in the middle there is more of the academic administrative buildings. They have some, to the north along the lake, they have some residential buildings again, and then some more kind of mixed use there in the east. But when we looked at comparing clustered approach to centralized approach, we showed that if you get rid of the central plants, which you would have to build new buildings potentially, you got to look at, is there space in the existing buildings for heat pumps that can serve all these buildings as opposed to just one building. But then if you also want redundancy on those heat pumps, backup boilers, peaking boilers, things like that, you're likely looking at building new central energy plants. And then compare that to the cost of just these yellow connections of one large centralized and just laying pipes to connect these networks together. So that was a good approach that, we showed that it was cheaper net value over 25-year life of the system. But electrical demand impact, the orange line is what their existing capacity is. The blue bars is what their existing peak demand is in the wintertime. And then the green is what peak demand we're adding on top of that. So you can see there's, in a few scenarios where we're using natural gas, they have additional capacity, so they're not overloading their system. They don't need to do any upgrades. They still may want to do some upgrades because of redundancy issues and things like that, because they're kind of maxing out their redundancy as it is on their existing systems. But it just shows that they didn't necessarily need to undergo additional capacity increases by doing the natural gas backup and peaking scenarios. But if you're looking at electric boilers, that was a significant impact where you're going to have some significant electrical upgrades, and then getting into what the grid can provide is a different story that we didn't necessarily look at. Kind of would be a next step if they were to go that route. Another thing we wanted to look at was, are building upgrades necessary to transition to low temperature water? Right now they're a steam-based distribution, but inside the buildings they're all hydronics. There's not any steaming coils or anything like that within the building. This is sort of another hybrid approach, instead of looking at strictly peaking and backup, but looking at what temperatures you're producing and what equipment is producing those temperatures. So with a reset schedule, where you're producing 180 during the colder periods and then dropping that down to 140, we can set when the heat pumps will operate. So they're going to operate, we put a cutoff at 165 degrees, which you saw some examples earlier where they're producing 165, or the heat pumps are producing 165. So those will operate up to 165, and then they'll shut off, and the peaking boilers will take over for anything above 180 that's needed. And so when that's the case, the ground source heat pump operates 90% of the year, and they provide 80% of the thermal load. And then the peaking boilers are only operating that 10% of the year and 20% of the load. So it's another strategy as opposed to just strictly looking at peaking and baseload. So they don't necessarily need to change all their coils to 140 degrees. They can get by with what their existing equipment is until they get to those renovations, because it doesn't pay back necessarily to do those up front and include that cost into your heat pump plant. It improves the efficiency, and we want that to happen over time, but it's not necessary to start the transition.
I may just add to what Joe's saying too. Oh, which part was I going to say to that? Yeah, it'll come back to me.
And then Rob, you were going to talk about
Yeah.
an ambient example.
Oh, I knew. All right, now I remember. So I just had to get out of my seat. So to pick up on what Joe was saying for the campuses, they're going through their facility master plans, usually on a 10-year basis. You can only fit so many projects into these master plans. There's only so much renovation you can do over time. There's only so much funds that the state has to be able to do this work. So if we can get kind of going in that vein of working towards this, and then SUNY's their own goals are any type of major renovation, whether it's a partial or a deep energy retrofit, they're at least 140 or lower. So like Joe said, eventually it'll keep coming down, but in the interest of trying to make progress, we can get to this base load and peaking and still be able to make advancements. So couple example projects here that you might find of interest. And it looks like something, oh, that's weird. The image is not showing up. Okay. This was a study that we did for Madrid. My UK colleagues worked on this. It was a, multiple consumer classes. It's kind of small font over on the right, but residential, commercial, health, there's educational, various components worked in there. The client was very much interested in an ambient loop system. So fundamentally, we looked at this in two approaches. So an ambient loop with active and passive balancing, and also tied back and forth with a fourth generation, multiple fourth generation systems working off the loop. There was two different configurations for this. So you can see the one on the left is an ambient loop, and then there's fourth generation systems kind of scattered around it with geothermal storage involved in that one. And then on the right is an ambient loop. No, hold on, let me check my notes. What was the second? Sorry. Yeah, those are all ambient. That's full ambient networks on the right side. So what was important for this one is they did not have simultaneous heating and cooling, and it was they were finding it really difficult to try to balance the system out without having that. So there's seasonal dynamics that played into it. There was only a 5-degree delta in the system, and they tried to look at it from an aquifer thermal energy storage potential and a borehole thermal energy storage potential, but they just didn't have the storage capacity within the geology to make it work. So ultimately, this ended up just being what it was. It was a study to show, was it viable or not? It didn't advance into the design phase, and the client still is assessing potential options on that. So what they, basically they were the interest in this hybrid approach here was they were just looking at it from a phased construction and kind of economic development standpoint. So the client was solely driving the discussion, and we were just helping them make a decision on it. And then this is an aquifer thermal energy storage test case here. Hillerød is a city in Denmark. It's pretty cool. If you ever get a chance to go there, I got to visit this one. It's got a really cool castle with really nice grounds that you can walk around. So if you're ever up there, put this one on your list to do. Looks like it went. Oh, that's weird. Something happened in the copying of. Okay, so anyway, I'll just keep going with it. It was drilled in 5 phases. Phases 1 through 3 were developed, but for whatever reason, they're not showing up on here, but they show up on mine. So they they drilled in 3 phases and then did some assessment and then continued to drill after that. Basically, they were just looking to optimize where in the subsurface was the best area for this. You can see from these photos, or from this image, at the very bottom is grout. So they found that layer, that's kind of the second color up from the bottom, was the best area for the geo exchange. For the final ATIS well design, so it was considering the different flows. Initially, it went down to a depth of about 400 feet, but the yield was too low. So the final is at about roughly 250 or so feet, 71 meters. I didn't do the exact calc on that one. Oh, it does have sound. Oh, cool. So that's the hydraulic test. Considerations. There's a NYSERDA report that came out recently on aquifer thermal energy storage that was released, largely studying the New York City area, in that general area, so look for that. It has some good information. With this one, it's really about what to do with the amount of water. So this was like 13,000 to 26,000 gallons. Per hour. All right. So per hour, they had to figure out what to do with this. They couldn't get a permit, so they had to basically take it out of one well and then push it right back into the other well. So normally you would do a test like this for 7 to 14 days. They can only do it over the course of 3 days. So there's the permitting aspects. There is the logistical aspects. They wanted to assess the temperature changes after 3 years. High yielding boreholes, testing them at a high flow. Conclusion is that for the flow need to be reduced, or additional boreholes would be needed. So. Sorry, some of my slides I just had a format going that did not show up the way it was supposed to. So, basically, what you're not seeing here is a different image popped into it, which I don't know why, but they did some free flow modeling, and the wells were too close to each other. After 3 years, there was going to be an impact. So the test wells were important in designing what that future layout would be, and then spacing them out further after that. So, Joe. Not sure why some of those didn't work.
Rob, just a time check. We got about 10 minutes left.
Okay. I think this is our last slide. So transitioning to this electrification, it's a phased approach. It's not going to happen all at once. So do the campuses or buildings need to convert from steam to hot water? What's needed to be done? Does it have to be, do you need building improvements, HVAC replacements, coil replacements? You're probably going to have to redo, if you have a district system that's steam-based, you're going to have to rerun your district lines for low temperature water. But all in all, we want to utilize the existing assets they have in this transition phase, and it'll be a heavy hybrid approach where we're utilizing natural gas or fossil fuels in addition to electrification, and achieving as much decarbonization as we can cost effectively. Incorporating those electrification technologies with thermal storage as well. Operational, it's going to depend on external influences such as fuel and electric prices, whether you can co-produce heating and cooling and maximizing your COPs, but also the expected fluctuation in electric prices based on your intermittent renewables, and utilizing those renewables and your electrification when it's high, and then utilizing storage and minimizing fossil fuel when that production is low. And then, as all cases, new skills are going to be required for the staff operating that equipment. It's quite different than a steam boiler, so the staff's going to have to be trained up, as well as everyone building the central plants and laying the pipes and everything. So I think that was all we had. So we can open up to questions.
Questions?
Hi guys, a good presentation, interesting case studies there. Just a quick question and then a comment. The quick version of the question is, how are you defining a hybrid system? And I think what I'm getting from the presentation is the peaking component that's still coming from some fossil fuel mix is what's defining the hybrid nature of it. There were some examples where even in a geothermal conference, there was no geothermal component in some of those mixes, but still with 100% energy mix of various renewable sources, are you still considering that a hybrid? And just a quick comment, in no way am I endorsing natural gas use. I think this is certainly the path forward, but I shouldn't say poor gas utilities, but gas utilities have trillions of dollars of sunk assets across the world that probably deserve to amortize that over a little bit more time. So this hybrid approach of using that existing infrastructure is probably a wise path forward in the near future.
Yeah, thanks for the comment. When John asked us to, hey, I've got this opportunity for you to present, it's on hybrid, right? So we weren't sure, did he mean like hybrid residential? So no, I think it's really hybrid in our case. I think for what we're talking about today is just really sector coupling and looking at multiple ways of doing this. Before a few years ago, there weren't many, at least stateside, we weren't talking about wastewater plants that much in terms of a waste heat source or a data center. So if we can use a abundant heat source that's readily available and captured and can save us money in terms of the overall economics of the project, that's kind of like what the hybrid approach is going to be. I would say for most of the SUNY campuses, many of these things, we don't have that opportunity. It's really going to be arguably a ground source will be there, or a combination, and Joe had that one slide that showed the different scenarios with SUNY Oswego, but there were air source. Maybe you can speak to what those were, the types.
Yeah, we looked at a combination of
Go back up to that slide.
Using air source and water together. It would be the same heat pump, it'd be a water-to-water heat pump, but that on the air side, it would just be a water loop that goes to dry coolers to capture heat from the ambient. So you're not putting in multiple heat pumps, it's the same heat pump, just capturing from different sources and diversifying what your sources are. It helps with the balancing standpoint. The campus, it has the opportunity to provide cooling to every building, but not every building is set up for cooling, but every building is set up for heating. So certain campuses might be a little bit more balanced than others. Some are really unbalanced. So utilizing other sources helps with that balancing of the bore field. So whether it's air or wastewater or surface water, it just helps with the balancing. You can even use that source directly inject it, into the loops as a heat source to balance the loops instead of taking load off of the bore field, depending on how the operation is set up. Back.
Hi, I was under the impression that you would be limited as to accessing external resources to support and offset the expense with a hybrid system. We were told anything that's fossilized, so to speak, in the project as you're renovating will cut your the incentives that come from NYSERDA and or the government or whatever else that's offering it. Are you running into that?
I think a lot of the projects we're looking at, they're existing assets. So.
Well, you're.
Existing still apply for the incentives and receive them?
Sorry.
I'm not sure as far as incentives go.
I think he's talking about project like buildings, but your hybrid system is more about the district.
Yeah, we're looking. Yeah, we're looking at district level as opposed to building level.
You mentioned it
So-
at the Oswego site that they were going to keep some of their boiler systems.
Yeah, so they have one large central plant of boilers instead of individual boilers around the building. It's a centralized system.
And that won't count against them when they go looking for incentives to support their geothermal network?
Counting against them in what way?
Money, incentives that come from NYSERDA, all the different programs.
It's an existing asset. It's
Yeah, I mean, I'm not sure the NYSERDA rules and what pond. I guess that depends on what pond.
is the
right?
question if they continued to use the central plant for whatever reason, whether that would be held against them for getting incentives for a new
Yes.
heat pump. I don't know the answer to that question.
Okay, I'm at another SUNY, and that's what we were told, that you gotta get rid of that stuff, or your incentive goes way down.
Well, yeah. So we can talk maybe after about what the incentive is, but yeah, we're really familiar with 1B-2 and what's required with that directive as well.
I can say more than 50% of the energy of your system needs to be from GEO in order to get like the IRA credits. So if you have a hybrid system and say you have 40% air source, 60% GEO, you can still get it has to be over 50% for the IRA credits. I know that's a.
Okay.
Thank you.
Yeah, thank you.
Thank you. It's Aaron from National Grid. I was curious, it looked like you'd mentioned that a lot of these campus-wide systems or larger district systems were double pipe systems. Is that accurate? Or is it one like return and one supply pipe versus a singular system?
Most of them,
I
two
think
pipes now.
A lot of them were two pipes, so supply and return, and then they would have some switchover point from heating to cooling. But I think a lot of the studies we've looked at have also been four pipe, so separate heating and separate cooling supply and returns.
The thought of using the two pipe system for 2 seasons came up, but then the longer we talked to the campuses about it, they were really concerned about shoulder seasons, and some of them flat out, because some of them right now are just like, okay, May 15th we're shutting it down, and then we restart it September, whatever the date is, right? So it's down the whole time. So if you used it during that time and used it for a cooling network, that's what we're trying to look for ways to help it.
Mm-hmm.
But some of the campuses just flat out said, we don't want it. We would just rather put the extra money into it and then have that flexibility because the shoulder seasons are becoming maybe a little more erratic or a little longer.
I think
Are
some
there-
of the examples we looked at just didn't have a lot of simultaneous heating and cooling load. I mean, that could change as campuses or communities add more cooling to their portfolio. But based on the data we had, there just wasn't a lot of hours where there was simultaneous loads. But
So is it-
that could change. And then, as looking at future weather forecasting, what is that going to look like? And as,
So is there
more and
a
more cooling's added.
a specific variable where double pipe systems perform better? Is it that simultaneous cooling and heating?
Yeah, I think it's more of a cost
Okay.
exercise than a performance exercise from what we see.
Thank you.
Okay, well, Robert and Joseph, thank you very much. How about a round of applause?